Okay, so good afternoon for this eighth lecture in CFD for this year. As I was just saying, we have a full program this week. Today we will conclude the numerics part, or the basic numerics part, and starting with tomorrow, I think we will then look at compressible flows and the specifics of the equations there. But essentially today we would like to look at von Neumann stability, the kind of the most common stability analysis that we do for different CFD methods, and then kind of trying to wrap up also that chapter by comparing the various approaches that we have looked at for stability. In order to do so, I thought I will start with a short summary of what we have done last week in the course. And I guess the main topic that we looked at in the last lecture was the stability of an ODE. An ODE, we just take here this simple equation, the Dahlquist equation, U prime is lambda times U. And then we try to see under what circumstances this equation or the time discretization is stable for this equation. We chose, as the first example, we chose the Euler forward scheme, which then can be written in this way, that un plus 1 divided by un. So that means essentially the amplification factor, if you go from one time step to the next time step, is then something like 1 plus delta t times lambda. Lambda, of course, that's this coefficient that we have in the Dahlquist equation. What we have then done is to introduce an abbreviation, this Z for, I'll just take away the colors here so that it's maybe a bit easier to see. Wait, that was a bit too much. So we have introduced the abbreviation Z for this lambda t times lambda, which is a non-dimensional number. And with this, we could then write the amplification factor, which corresponds to the forward Euler scheme as being 1 plus Z. And this equation or this expression is actually quite an important expression that characterizes the Euler forward scheme. And sometimes this is called also the characteristic equation that belongs to the Euler forward scheme, because essentially it tells you what how the solution will be changed from time step n to time step n plus 1. So the amplification that you get from one time to the other is 1 plus Z in this case. And then we try to understand what this 1 plus Z or this amplification factor really means in terms of stability. If you remember, we said that the absolute value of this 1 plus Z needs to be bounded by 1 in order to avoid errors to amplify. And then we realized that the region where this is fulfilled, so where it's fulfilled that the absolute value of G is below 1, lies inside a unit circle located at the -1. So in this region here in the set, in the complex set space. So that means if I want to do an integration that is stable, I need to choose my lambda times delta t in such a way that it lies somewhere inside this circle. If it's outside, then my integration will be unstable. Of course, that directly means, if you look at it, if lambda is positive, so if lambda lies in the positive half plane, then we can see that this is not possible because delta t, of course, needs to be a positive real number. It's a time step, it's a physical quantity of a time. So that means it's not possible to find a corresponding delta t that would bring me back into this unit circle. But on the other hand, if the real part of lambda is negative, then I can typically find a sufficiently small time step that I end up in this unit circle and I can get a stable integration. Stable, I mean numerically stable. Analytically, everything with lambda minus lambda negative would be stable anyway, because it's an exponentially decaying solution in any case. Okay, so this was the stability of the ODE that we looked at, and we have also, if you remember, we have looked at a corresponding case. We have looked at the corresponding case also of the implicit Euler. Maybe I can just very quickly add that here as well. So we also looked at the implicit Euler situation, where we then found that un plus 1 minus, divided by un was something like 1 divided by 1 minus z as the characteristic equation. And for this, we saw that this also corresponds to a unit circle, but this unit circle actually lies on the positive side. This again is the real part of z, and this is the imaginary part of z. So that means everything outside of this unit circle was stable. So that means that this scheme was actually something that we call astable, meaning that the complete left half plane can be stably integrated with an implicit Euler scheme. We will get back to that property later on as well today. Okay, so that was the first bit that we discussed last time. The second part, and also where we now continue, was the von Neumann analysis that we could perform on a complete partial differential equation. So not just on this ODE, the Dahlquist equation, but the von Neumann analysis can then be performed on a complete partial differential equation, so with both spatial and the temporal dependency. And the idea there was that we introduce a Fourier transform and we assume linearity, which then allows us to consider each individual Fourier mode separately and determine the stability for each mode independently. That makes, of course, a great simplification. And where we are right now was essentially at the position where we introduced our ansatz, which essentially says that our UJN, J being the spatial discretization or position, and N the temporal one, can then be represented as a Fourier transform or decomposition, where we do effectively a separation into time and space. Time is represented by the complex Fourier coefficient u hat kn. I'm typically using the notation that a hat on top of a letter means that it's a Fourier transform quantity. K indicates the wave number that is associated to that Fourier mode, and of course the n is the temporal dependence. And then we have the spatial dependence, which is e to the I kxj, and these are the Fourier modes, so sines and cosines, or as written here in terms of the complex exponential. The interesting thing here is that the e to the I kxj, these are spatially fixed basis functions, so they do not change as my simulation propagates. They're fixed. They're fixed base functions. The only thing that changes as a function of time are the Fourier coefficients u hat kn. Now, as I said, because of linearity, which we need to assume for the von Neumann analysis, we don't actually need to consider this whole sum here over all the Fourier coefficients. We can actually just consider one single mode at a time, and then just make sure that the stability holds for all the Fourier modes. But we actually do not need to consider a whole sum. So therefore, that was the last thing that we did last time. We could then say we consider an individual mode, which can be written in the way that is indicated in yellow here. Okay, so that's as far as we got last time. So I would like to ask you whether there is any question so far about either the stability of the ODE or the von Neumann analysis so far. Okay, but then I guess we can just continue from that point on. Now the idea is, now we have this individual mode, and now we just need to essentially go back to what we mean with stability. So we can now define an amplification factor, which is very similar to the one that we introduced for the ODE, just with the difference that we say that it's the relation between two Fourier modes u hat k at n plus 1 divided by u hat k at n. So essentially the amplification of one Fourier mode from time step n to n plus 1. And this amplification factor we can then again call g, and to express the fact that we actually look at the amplification in Fourier space, we can call it g hat. And also maybe just to kind of be a bit more precise here, we can say that this amplification factor is in fact a function of k, a function of wave number. So we need to make sure that we calculate this amplification for each wave number, each spatial wave number. So it's g hat of k. And now with this amplification factor, we can go back to our definition of stability. And so condition for stability. And it actually turns out that it's the same idea. We also don't want disturbances or errors to amplify. So we also need to say that the absolute value of this g hat k needs to be lower equal 1. That's essentially it. But now, because this is still a dependence of k, we need to say that the maximum over all wave numbers of this g hat k needs to be lower equal 1. In fact, there is another addition that we can do here. We can, in fact, allow disturbances to grow linearly in time, so not exponentially, but linearly in terms of this g hat. This would then still be sufficient for stability from the von Neumann analysis. But this is kind of a slight detail, and it's in practice typically not relevant for us. So just consider essentially the idea here that the maximum of the amplification needs to be bounded by 1. So we don't want individual Fourier modes to get larger and larger as time propagates. This delta t, this order of delta t, this comes from the fact that sometimes you have linear terms in your equations, which then will give you a growth over time. But this is perfectly okay and will not harm the stability. So think, for instance, of a problem with heat transfer where you have a constant heating in the domain. And that constant heating would essentially give you an increase over time, but this has nothing to do with the amplification of errors. So therefore, you have this additional term. But essentially, this is already everything about the von Neumann stability analysis. So we introduce an individual mode, we define an amplification factor, and make sure that it's bounded by 1. Let's make an example for that, just to kind of see how this would be done in practice. Of course, I guess you guess it by now. The example that we would look at is the advection equation. The advection equation with the forward time, backward space discretization. So if I directly write down the fully discretized form, so we have ujn plus 1 minus ujn divided by delta t plus a times ujn minus uj minus 1n divided by delta x is 0. So this is the fully discretized version of the forward time backward space scheme. And as I said, for the von Neumann analysis, we look at the fully discretized equation. So we're not looking at an ODE or some test equation. We directly look at what we would implement in our simulation code, for instance. And now the idea is that we need to replace our solution, so these guys here, with individual Fourier modes. So essentially with what we have written here in yellow. So that means if we now do that for all the terms that we need, of course, the ujn, that would just be u hat k at time n times e to the ikxj. So there's no problem with that. But now uj n plus 1. So if you go one step ahead in time, of course, that would be essentially the same. You had k, but then you have n plus 1 here times e to the I k xj. So there's no change in the spatial part, but there is a difference in the temporal part. And then the other term that we need is uj minus 1 n. And here we need to change something in the exponential. So we would write like this. This is u hat kn times e to the I k. And now it becomes xj minus 1. But of course, this I can now replace or change with the help of the spatial step delta x. So that would become something like this: u hat kn times e to the I k xj minus delta x. As I go, to j minus 1, so I need to subtract delta x. And now, just with the rules of exponentials, this would be e to the I k xj times e to the I k delta x with a minus sign. And of course, what you see now is that this here is essentially the same as u hat uj n. So you see now what happens if I go in a spatial direction. I just take my uj n and multiply it with e to the minus I k delta x. That's essentially the effect of the Fourier transform that I have. Okay. Yeah, now I just need to take all these terms and I need to plug them into my fully discretized version, as simple as that. So if I just kind of show that, this would go here, this guy would go here, this guy would go here, and this guy would go here. It's as simple as that. Now, I'm not going to do this calculation, but what I get in the end, if I do this combination, my result will be something like that. U hat kn plus 1 is U hat kn times 1 minus delta t divided by delta x times a times 1 minus e to the minus I k delta x. Something like that. So this is when I put everything together. And now the next step for my von Neumann analysis is that I need to calculate this spectral amplification factor g hat k, which is u hat kn plus 1 divided by u hat kn. And of course, that's exactly what you see here. So imagine I divide this by u hat k, or I can do that. So it's like this, u hat kn, if I just divide it. And of course, this is exactly this g hat k. Yeah, and essentially this is, well, we're nearly there. What we see here is that we have one part down here, which is dependent on k and delta x, but then we also have a prefactor, this delta t times a divided by delta x. And a typical abbreviation for that is to use sigma. For this term, delta t times a divided by delta x. And it turns out that this is actually a dimensionless number because you see a is a speed and you normalize this speed by delta t and delta x. So this becomes a non-dimensional number. So with all of this, we can then write our g hat of k is simply 1 minus sigma times 1 minus e to the minus I k delta x. So this here, so the last expression is now my spectral amplification factor for the forward time backward space scheme applied to the advection equation. Okay, so what do we do now? Now we need to understand whether this is stable or not. And the condition for stability was that the absolute value of this needs to be lower equal 1. So for stability, and the idea is that this g hat of k needs to be lower equal 1. So we need to somehow get an understanding how this looks like in spectral in complex space. So what does it actually mean for my time step delta t, which now seems to be encoded in the sigma. So the time step is located in here. So we kind of do the same thing as we did before. We try to plot this in a real and imaginary space, with real and imaginary axis. So we directly plot the amplitude of this g. And now it's maybe nice to identify how this actually looks like. This is 1 minus sigma. If I write it down, this is 1 minus sigma plus sigma times e to the minus ik delta x. Now you can wonder what this here is. Well, this corresponds to a circle. So the circle is this guy with radius sigma, this one here, and a center at 1 minus sigma. So if I have one here and one here, so I said it's a circle with radius sigma with a center at 1 minus sigma. So for instance, the center is here, then this one would be 1 minus sigma, or this position is 1 minus sigma, and then I need to have a circle with a radius of sigma, so something like this. So this red line corresponds now to my g hat of k. Now stability, if I now use green, the limit for stability is what I now indicated with green. So that is that g hat of k needs to be lower equal 1. So you can kind of indicate this in this plot. This would be okay, that's not a very nice circle. But the stability now, sorry, stability would now be a circle. It's even worse. Circle with radius 1. That corresponds to the stability criterion. So essentially, g absolute value lower equal 1. And now, the condition for Neumann stability means that whatever I get from my discretization, so whatever I get as my amplification factor, so the red bits, need to be fully enclosed into the limit that is given by the stability. So the red curve needs to be fully enclosed by the green curve. And if this is the case, I have a stable integration. So if you write that down, so for stability, we need to have if I'm writing it a little bit sloppily, or we can write it like this. We need to have g hat of k fully inside the circle with a radius of 1. If this is the case, actually I don't need the g of hat. It's just z. So the absolute value of z equals 1. If this is the case, then I know that the stability criterion is fulfilled for each k, because the parameterization of k that I have in my g hat of k is essentially along this circle here. And of course, if I now go into a little bit in more detail, I see that if this is so the sigma is the position and the radius. So for what sigmas is it actually so that this red circle is inside the green circle? Well, then I see that I can start at 0, then I have a very small circle here, but this is fully enclosed, and then I can increase the radius of the red circle up to the point that sigma equals 1, because then the center would be here in the middle, and the red circle and the green circle would just coincide. But that is then the highest value of sigma that I can choose before the system becomes unstable. So that means if I just do that graphically here, the stability limit would then become sigma must be lower or equal 1. Or if I now use the abbreviation that I've introduced for sigma, namely sigma being delta t times a divided by delta x, it just means that a times delta t divided by delta x needs to be lower or equal 1. Or if I calculate that directly for a time step, my delta t needs to be lower or equal delta x divided by a. So this here would now be my stability limit for the forward time backward space discretization applied to the convection or advection equation. Whenever my delta t is smaller than that limit, so it fulfills this condition, then my integration is such that the spectral amplification factor is below 1, which is good. And as soon as my delta t is a bit larger than this expression, I would expect to have an unstable integration. Now there is a question in the chat. Can you please say the definition of the amplification factor again? Amplification factor is defined in terms of the error. Okay, so the definition of the amplification is given up here. So this here would be my spectral amplification factor. And it just says that for one time step, my u hat k, so the Fourier coefficient for wave number k, is growing by this factor g hat. And this is really from one time step to another as a function of k. And that is, of course, very similar to what we did for the ODE, when we also said from one time to the next time, we allow a specific growth to happen, or we get a specific growth. So this is just now written in spectral space for each wave number k independently. So this is the amplification factor. And now, this, of course, is written in terms of u, of the solution u. But as we have seen before, it's the same equation that also is valid for the errors. So you can also view this as being the amplification factor for errors. So error epsilon k hat at times n divided by epsilon hat k at n. So it doesn't matter whether we consider this to be errors or the solution. Both of them fulfill the same equation if we consider them to be linear error, which of course is not fully true perhaps, but that's what we base it on. So the amplification factor is both for errors but also for the solution, and it just comes from the discretization scheme. Now there was another question: how would the value of A change with different PDEs? The value of A, here we have the advection equation. Well, the value of A essentially comes from the equation. So we say that the equation that we want to solve is this one here, du dt plus A times du dx. That's the equation that we would like to integrate in time. And at that stage, A is an input parameter. That's just a number that we give. It's the convection speed in the advection equation. So it could be 1 meter per second, 10 meters per second. Of course, the relevance of this A comes later on, if we then go into for instance, Navier-Stokes or the Burgers equation. But if we just think of 1D Navier-Stokes, then this term would look like this: du dt plus u times du dx. Du dx is, and then you have some pressure terms and viscous terms and other things. Then, of course, in this situation, this convection speed would actually depend on the actual solution. But as you see here, this is then a nonlinear problem because you have u and u, and formally speaking, you cannot use the von Neumann analysis to treat this one because it's nonlinear. So you cannot just do a Fourier transform and then consider individual modes because they would actually interact with each other. But this problem can be solved, and this problem can be solved with linearization, which we will look at later on as well. Okay. Good. Yeah. So exactly. So this is now the von Neumann analysis on the example of the advection equation. So you calculate the spectral amplification factor, in this case 1 minus sigma times 1 minus this e to the ik delta x, and then you just make sure that this amplification factor is fully contained within the unit circle located at 0, 0. And if this is the case, then we know that for each wave number k, I will have a stable integration. And if I do that for this particular combination of equation and discretization method, the solution will then be in a limitation of my time step to be delta t lower equal delta x divided by a. And what you can directly see from this is that if my spatial discretization goes down, so my grid spacing goes down, so my delta x goes down, my delta t also goes down, which is something that you probably all know. If I refine my mesh, my time step also needs to go down. At the same time, if my speed, the a, goes up, so I have a problem where my velocities are higher, also then my time step goes down. So if the a goes down, then my limitation of the delta t goes down as well. And of course, there's a physical interpretation behind that. But this we will look at later on, or actually we can mention it already here. So this is, I call it similar for the time being, similar to the so-called CFL condition for convectively dominated problems. CFL comes from 3 people that worked on that. That was Courant as one person. F comes from Friedrichs, and L comes from Levy. And they did that in a, I would say, groundbreaking paper in 1920 when they introduced exactly this issue of the time step being actually limited by delta t by delta x and the convection speed. However, they did it in a slightly different way, which we will look at later on as well. So this condition here can be called the CFL condition, and the sigma, which was as we introduced up here, so a times delta t divided by delta x. This is typically called the Courant number, like the Courant number that we then have for a time integration. So that combines the speed, the delta t, and the delta x. Sometimes we call it also the CFL number, but in principle, it would be the Courant number and the CFL condition. Okay, now I would like to actually show you the relevance of exactly this Neumann stability result. And for this, I would like to switch to MATLAB because I have prepared a little demonstration, and I hope that I can make this work. And that's always a little bit of a problem. So let me see whether this works. Okay, no, it seems not to work. Where's the figure? Ah, here I have a figure. Okay, can you see my MATLAB figure? Maybe not. I need to see what I'm sharing.
No.
Okay, then I shared the wrong thing. I need to share the screen, the whole screen. So like this. Now you see a MATLAB figure in the middle, right?
Yes.
Okay, very good. So what I would like to show you here is the following. Essentially, it's something that you also need to do in homework later on. But I think it's very important to kind of demonstrate this also in the lecture. So we have here a diagram where we have time-dependent. Actually, this is wrong. It's not t. It's actually x here. I'm sorry. I added the x's this morning, so it was actually wrong. So now it's better. Okay. Now, what I would like to show you here is the evolution of an initial condition, which is this red dashed line, kind of a top hat function, just 0, then it goes up to 1 and then to 0 again. And I would like to show you the time evolution of this initial condition under the effect of the advection equation as a function of time. And of course, what you would expect here is, because it's an advection equation, you expect this initial condition to start at wherever it starts, and then just to move in the positive x direction. And of course, that's what it does. If I play that again, this is for the exact solution. It just starts here and travels in the positive direction. Okay. So this is the exact solution, which I can calculate as we did a few lectures ago, just by following the characteristics backwards in time. But now the question is, what happens if I discretize that the advection equation exactly with the forward time backward space scheme as we have just discussed? So I do that, and I can just briefly show you the code. In the end, it's a very simple code. Somewhere I have a time loop, and then I have this rule. I update u1 is u0 times minus dt divided by delta x times a, and so on. So there is so that's just a discretization I have. Now the question is, how is the solution then dependent on the choice of my Courant number? So this a times delta t divided by delta x. So I show you a first run, the first example. Now I can just write it like this. So, or demonstration rather. So demonstration, if I choose sigma to be 1. That's maybe the first question. What happens if I choose sigma equals 1? Well, that's actually something that we could even analytically look at. If I just go up to, where's my fully discretized? Here is my fully discretized version. Let me just write that down again. So uj n plus 1 minus ujn divided by delta t plus a times, what did I have? ujn minus uj minus 1n divided by delta x being 0. Okay, and now if I just write that in as a so that I just get ujn plus 1, what do I get? ujn minus, now I need to be careful that I'm doing it right, minus a times delta t divided by delta x times ujn minus uj minus 1n. Did this go wrong? I think that's correct, right? Now, if I choose sigma to be 1, so then of course this one will become 1. And my result here will be, so ujn plus 1 is, well, if this is 1, then this and this, they take out each other, and then this becomes a plus. So it will just be uj minus 1n. So that's now the exact solution of my discretized equation. And of course, what does that mean? That means that my solution at the next time level is just the moved by one grid point solution of my previous time level. But keep in mind that I chose, in this case, my delta t exactly in the way that sigma is 1. So the speed that I can construct with delta x and delta t is exactly the speed that I would have. So if I plot that, if this is my characteristic, so the slope a, then this is delta x and this is delta t. So I have exactly kind of reconstructed the slope of the characteristics with the help of delta x and delta t. So that means that this would actually give me my exact solution of the partial differential equation. So I have actually here a way of getting the exact solution by means of my discretization. So that means if I choose in my code sigma to be 1, I will recover the exact solution. And of course, I can demonstrate you that by just running my code with sigma equals 1. And that's what I do here. Sigma or s in my code, I set it to 1. And if I run this, well, that's what I get. That's my exact solution. So that means sigma being 1 is, well, first of all, it's stable, and it gives my exact solution. Okay, now of course we can go back to this graph that I did here. Well, if you remember what it means, sigma being 1, well, the red circle would lie exactly on the green circle. So meaning that the spectral amplification factor for each Fourier mode is exactly 1. So that means that the amplitudes of the Fourier modes are actually not changed from one time step to another. The only thing that may be changed is the phase. So the amplitude is not changed, but the phases may change. And change of phase in Fourier means, you know, a translation in physical space. And of course, that's exactly what happens. Since the amplitudes are untouched, I just translate in physical space. And well, that's what I got. I can just play it once more. That's a translation in physical space. So everything is kind of consistent, and I get exactly the results that I want. Okay, now just before the break, I would also like to show you what happens if I now start to modify my sigma. So if I go from 1.0 maybe to 0.5. So I have a CFL number of 0.5. So I make essentially my time step half as large as it could be from compared to the stability limit. So meaning that I'm not being on the unit circle with my spectral amplification factor, but I'm having a circle with only 1/2 as the radius. And I guess you already understand now what happens, because that means that I'm actually you know, I have an amplification which is less than what it should be. So that means that most probably the amplitudes of some of my modes is decreasing. Let me just plot that, or let me just play that. Well, I start with my initial condition, and I guess what you see here is, well, you see two things. First of all, it goes slower. The reason why it goes slower is because my time step is only half as large. But you also see that the shape is not this nice rectangle anymore, but it's kind of a diffused blob. And of course, the reason why it's diffused in that way is that we have not an amplification of 1 for the amplitudes of the Fourier modes, but we actually have a lower amplification, meaning that everything is kind of smeared out. Okay, but with this, I guess we can take a break of 15 minutes. And then after the break, we also see what happens if we go the other direction, if we increase sigma, to see whether or not it's actually stable or not. Okay, so welcome back to the second hour. Just before the break, we ran a few cases where we had sigma being lower 1 for the advection equation. I just like to run one more example when I choose sigma to be very low. So I take as an example 0.1 as sigma, and I just run it here on top of what I had here. Again, what you see is that it gets slower. It gets slower because the time step is now 10 times slower than what it could be. And also what you, okay, now it takes quite a while, but what you can, I guess, directly see that it's even more diffusive. The solution is even more diffusive in a sense that the very sharp initial condition is kind of, melting away on both sides. And you will see that more clearly when it then also comes to the final time, which I think I chose here as being 80 or so. And you will see that it's even more diffuse than the previous case, which was a sigma of 0.5. The reason why this is happening like that, we will discuss later on when we talk about the spectral representation of these time advancement schemes. But oh, yeah, okay. It didn't stop exactly at the same time. But you see that it has even diffused a little bit more. Okay, but now the question is, what happens if I choose a sigma which is actually above 1? So one that would be unstable. So I just clean this once more, and I run sigma being 1, just to have kind of our initial condition. Okay, now it runs. So this is the exact solution, or the solution with sigma being 1. Now, let's just take a sigma which is a little bit larger. Let's take sigma 1.1, just to try out. I guess the expectation would be that it's unstable, right? Let's see what happens. Oy. It kind of directly exploded. Exploded here. Exploded means that that essentially it has reached values that are infinity or not a number or something. And I guess now it even has crashed somewhere in the middle. So this was definitely a case that was not good. And this was for a sigma of 1.1. So let's just try something like this, 10 to the minus 7 or so. We run it again. Well, this kind of was stable. Okay, let's do a little bit less, maybe 10 to the minus 4, and we run it again. And then you see, well, there's some little humps here, but it kind of didn't explode yet. So let's now go into more detail, and let's now zoom in. It's a bit slow, it seems. Oh, sorry. So now you see what happens here exactly at the interface. You see kind of a wiggle appearing, which then is exponentially growing. And of course, this was only for a value of 1.0001. So 10 to the minus 4 or 5 larger than the stability limit. But yet I got I got already noticeable wiggles. And of course, if I go to 10 to the minus 1% higher, then it will blow up also very, very quickly. It directly blows up. So what you see from this is that this sigma being 1 is really a hard limit. So everything that is above 1 will directly explode. So this you cannot run. It will, all the errors that you get will directly explode. So from a numerical point of view, if you want to integrate this equation, so the advection equation, in a code, it's absolutely necessary to have this amplification factor to be below 1. Otherwise, it will just explode, as you have seen here. It may survive a little bit. That's what we have seen with the case where it was 10 to the minus 9, and that's kind of a representation of this 1 plus something that is c times delta t. So I can have a constant which is proportional to delta t in there, but everything else would directly blow up. Okay, so if I remove this from the screen, I can write down that for sigma being larger than 1, we directly get essentially a blow up. And what we can say here, and that's maybe the important thing to remember, that sigma lower equal 1 absolute value is a hard limit for stability. Okay. Do you have any questions regarding that? Okay. Let me do a second example here, a very kind of a straightforward example that we can directly continue. Example number 2. We do, well, essentially it's the same example. We do the same example, or same as example 1. Sorry. Same as example 1, but we say that a is lower than 0. So it's the same example. So that means we still have forward time, backward space. So we still have, if this is Tn and this is Tn plus 1, this is xj, this is xj minus 1, and these are my grid points. So I still have the upwind scheme in the sense that I'm using xj minus 1 and xj to get the xj point at the new time level. But now the difference is that the characteristics are like this. So they're kind of in the other direction than my upwind scheme is pointing at. Now let's see what the von Neumann stability analysis does in this case. Well, actually it's very simple. G hat of k is in fact exactly the same as before. It's 1 minus sigma, and then we have 1 minus e to the minus ik delta x. So there is no difference in the amplification factor. The only difference is a is now sigma, which was a times delta t divided by delta x, is now actually a negative number. So this is now below 0 because a is negative. Delta t and delta x, of course, need to be positive numbers. But now sigma is lower than 0. That's the only change that happened to the previous example. But of course, now we can go into the plot that we did before with these circles. And I'm trying to make them nicer circles. So we again have kind of the same situation as here. So we would like to plot the real part. This is the imaginary part. And we have the green circle, which would be absolute value of Z being 1, and that is the stability limit. But now the thing is that I also need to plot kind of this circle which has the center at 1 minus sigma with a radius of sigma. Well, but now the problem is sigma is lower than 1. So what means 1 minus sigma? Actually, it means 1 plus absolute value of sigma. So that means the center may actually be somewhere out there. So this distance would be 1 minus sigma, with sigma being negative. And then, of course, the circle would be something like this. This is still radius of absolute value of sigma. But now, of course, you see that this red circle is not within the green circle. It's essentially outside everywhere. And of course, that means that from the understanding that we have now gotten for the von Neumann analysis, that would mean that this integration would be unstable. So we can write down. So that means then that 1 minus sigma is actually larger than 1. So the red circle, the one that corresponds to the forward time backward space scheme, is outside. Outside of absolute value of Z being 1. So that means, simply put, we cannot find any combination of delta X and delta T for stability. So irrespective of how we choose delta T and delta X, our red circle will always be outside of the green circle. So whatever we do, it will be unstable. And in fact, this is kind of how should I say, the worst situation that we can have a numerical scheme, because that is something that is called unconditionally unstable. So irrespective of what we do, irrespective of how we choose delta X and delta T, it will be unstable. And of course, that's different to the case that we looked at here, where we got a limit for the time step. And of course, therefore, this condition here, we can say it's conditionally stable, with the condition that delta T is lower than delta X divided by A. So that's the condition. But whenever that is fulfilled, then it's stable, whereas this case here would be unconditionally unstable. But what was really the difference between the two cases? Well, the difference is the orientation of my upwind scheme, so the direction of how my scheme is angled, so xj minus 1 xj, so it's kind of a bias to the left, but my characteristics is kind of going in the other direction. So it's also going to the left, but my stencil goes to the right. That is the difference between the two different schemes, and it makes the second one to be unstable. So that gives us already one important hint, which we will later talk much more about, because that's then crucially relevant later on. It actually matters in what direction the information with the characteristic flows with respect to the shape of the stencil, the shape of how I choose my discretization points. Either it is conditionally stable, or it may be unconditionally unstable. Okay. So for now, I think that's what I wanted to say about kind of the von Neumann stability analysis. Of course, this can now be done for more complicated schemes, but the basic principle is always the same. You take the fully discretized equation and you plug in the Fourier transforms of the solution. The limitations, as I said, are this only works for linear problems because you do the superposition principle, so you just consider one Fourier mode. The boundary conditions are not considered because I assume to have periodic domains so that I can do the Fourier transform. And you need to have constant coefficients. Again, that's because of the separation of separation or the superposition principle. But once this is fulfilled, or can be made to be fulfilled by a suitable linearization, then the von Neumann analysis is a very helpful tool in order to determine stability. And most of our simulations codes, they use von Neumann analysis somewhere inside. Okay. Do you have any questions regarding stability? Okay, because then I would like to mention one last thing regarding stability, and that is something that at least confused me when I started to work a little bit more on that, and also maybe some previous students that took the similar course. And the thing was, what I never really understood at the time was, okay, now we had these two situations. We had for the ODE, for the Euler scheme, we had this circle here, remember, where this was a radius of 1, and this was kind of the real part of Z. This was the real part of Z, and this was the imaginary part of Z. And then we said, okay, it's stable inside here. And then what we just did now was kind of a similar plot where we had the von Neumann analysis, where we also had a circle, but then the circle kind of looked like this. And this was, again, some real part and some imaginary part. And what we learned was that it's kind of stable inside here. So this was something that always confused me. What's the relation between these two circles, let's say, and how could one maybe generalize it to also discretization schemes that are a little bit more complicated than just the Euler forward scheme that we have used now actually for the ODE and the von Neumann analysis. So I would like to very briefly show you the relation between these two circles and how to generalize that to also more complex cases. Okay, and this is actually a chapter which we have briefly mentioned before, but just as a side note, but I would like to spend a little bit on that here. And it's the method of lines which we would like to look at. In order to do that, we, of course, take exactly the same example again, because now we get more and more familiar with this advection equation, and it will also not be the last time that we use it, but still it's maybe good to take that, because we already know what we would expect from it. So advection equation, as before, du dt plus a times du dx is 0. And if you remember back, we talked about a semi-discretization when we introduced the time integration, when we kind of said that, well, we can do a semi-discretization so that we discretize space, but we leave time still in continuous. So we get the du dt is L of u. L is then some kind of spatial operator, and in this case it would be minus a times du dx. And now the idea with the semi-discretization was, if you remember, so that we can then write it in this way, that we have dy dt. So that's an ordinary differential equation with respect to the grid values ui, or uj. We can maybe take j. It's better. So we take uj, and I need to write it properly. This is now an ordinary differential. It's not a partial anymore. And this is then Ln, which is the discretized version of my grid values. And if I write it out, it's minus a times delta divided by delta x of uj minus 1. And this is, of course, for the backward space scheme here. So that's a semi discretization for backward space. Okay. So far, so good. Now, the idea here is we would like to kind of understand how we could connect the von Neumann analysis and the analysis of integrating an ODE. So the two concepts that we introduced before. And now what we see here is that, well, what do we need for this combination? So first of all, we have an ODE here. This is an ODE. But the problem is this ODE depends on uj and uj minus 1. So that's not very good. But with the help of the von Neumann analysis, we have now seen a way of kind of removing the spatial dependence. And of course, what we do is we do an ansatz, which is based on a Fourier transform. But so essentially we do exactly the same. So our uj is u hat k times e to the I xj k, as before, as for the von Neumann analysis. The only thing that you may recognize is that I'm not writing an n here. And the reason for that is that I'm still in the level of the semi-discretization, so I'm not actually doing a temporal discretization. So consider it to be continuous in time. Okay, but now I can do that. I can just plug in this ansatz into my semi-discretization, and if I do that, I get du hat k dt is minus a. And I'm doing now a few steps at once, but it's easy to follow them later. Minus a divided by delta x, and up here I have u hat k minus u hat k times e to the minus I delta x k. So I just plugged in the Fourier transform. Of course, this I can write now in the following way. Then I have e to the minus I k delta x minus 1 divided by delta x times u hat k. There must be an a somewhere, huh? There's an a here as well. So, okay. Yeah, but now that's actually, and that's exactly the point where I wanted to go. Now we're in the situation that we have du dt, du hat k dt is essentially lambda, one value, times u hat of k. So now I have formulated an ODE in u hat k. So that means now what I need to do in order for stability to hold, for stability for this ODE, I need to make sure that this lambda fulfills the conditions that I had for the ODE before. Okay. So what I should do now is essentially the following. I just need to make sure that this. So if I think back to the, if I think back to what we did with the ODE, but I need to make sure that I am if this is my circle here, would locate with the center at -1, and here I have the real part of Z, and I have the imaginary part of Z. I need to make sure that my Z being delta t times lambda is located somewhere inside this circle. And now my lambda is this term here. So e to the minus ik delta x minus 1 divided by delta x. So how does this look like? This my lambda times delta t. So I just write that. So lambda times delta t is essentially a times delta t divided by delta x times, I need to make sure that I make it right, e to the minus ik delta x minus 1. And of course, this guy here, we know from before, that's the sigma. That's the number that I already have termed to be the Courant number. So what is this again? This is a circle. Well, it's a circle with a center at minus sigma. Circle with center at minus sigma and radius. Wait, what is this? Radius sigma. So that means that it's maybe a circle like this. This is sigma, and this is a circle. And of course, now we're in the same situation as before. I can make this circle bigger and smaller with my choice of sigma. And in this case, I of course see that in order for being or to be in this green circle, to remain in the green circle, and the green circle that belongs to the explicit Euler. For this to be the case, I can scale my red circle up to the point that the radius is 1. So sigma is sigma, which is a times delta t divided by delta x, is lower equal 1, as before, or as we have now shown for a few cases. But now I hope you see the difference here. What we have done here is we actually we have calculated the stability based on the integration of an ODE. So the green circle now comes from the integration of the Dahlquist equation, u prime equals lambda u, which we have discretized with the explicit Euler. And the red circle comes from the spatial discretization. Okay? And we have compared those two. And in the end, this gives you then the connection between the von Neumann analysis and the ODE analysis. So you can kind of build upon the idea of the von Neumann analysis doing a Fourier transform, and you can put it into the framework of the stability of an ODE. Now, why is this actually interesting? There's two points that I would like to mention related. So first of all, so how to compute the lambda, or let's say the spatial operator that we have used here, namely this guy here. Do you have an idea of how one could calculate this? or well, well, we have calculated it here based on just putting in the Fourier mode into the equation. But maybe the question is different. Would you have an idea of how else we could calculate this? And this is kind of an open question to you. So if anybody can answer that, I'd be happy to hear a suggestion. So what we're looking for is kind of a Fourier representation of a finite difference scheme. Haven't we done that before in some way? Okay, well, so how can we compute this lambda? So we, if you remember back, at some point we analyzed finite difference schemes with the help of a Fourier mode, and that was in the context of the modified wave number. Because there we did essentially the same. We tried to see how the wave number, or how the derivative propagates in spectral space using a finite difference scheme. And now, of course, the question is, okay, in this case, we would like to have this finite difference scheme, which is backwards finite differences. So an upwind scheme. Now, how does the modified wave number look like for an upwind scheme? We have not calculated it, but you will calculate that in homework. I think it's homework number 3, where you will calculate it for forward differences. But now we actually need to have backward finite differences. But I just write down the result so you can confirm it yourself. So the modified wave number will essentially be ik tilde times delta x will be 1 minus e to the minus ik delta x. So this here is the modified wave number that we will get for the backward finite differences. So this is for backward space. And now the interesting thing is that this term is exactly the one that goes in here. So that is, I mean, with the minus sign, which comes from here, that is exactly the Fourier representation of the spatial operator, which is the modified wave number. It's nothing else than the modified wave number, because that's the modified wave number is the Fourier representation of the finite differences. So that means now we kind of start to combine different aspects. So we have calculated the modified wave number, and we can use the modified wave number to express the finite difference scheme. So in the semi-discretization, and then we have the time derivative, where we essentially can treat it as the integration of an ODE, and the stability limit of the ODE is, in this case, is the green circle, which corresponds to the forward Euler scheme. But that's my second comment. You can consider more complex time integration schemes. Integration schemes. So think of, for instance, a Runge-Kutta scheme. So if you plot again, this is kind of the same plot. We have here the real part of Z, and here we have the imaginary part of Z. And if we now plot a Runge-Kutta, an RK4 scheme, which you will, so Runge-Kutta of fourth order, or RK4, which you will look at in homework. I guess this will be homework number 4, if I remember well, where you look at the absolute stability of a Runge-Kutta scheme. There, it turns out that the region of absolute stability is not a circle, but it's kind of, I'm trying to draw it, something like that, where this value is at 2.8, and this one, I guess, is at minus 2.7. So it's considerably bigger than this the circle that we had here, the unit circle, where this, well, it's maybe slightly different scales, but something like this maybe, where this one was at -2. But now the interesting thing is, if you would now instead consider a time integration with the help of a Runge-Kutta scheme rather than an Euler forward, you would, in this plot, you would still have the same red curve, which corresponds to the spatial discretization, but now you had to fit it into this blue curve, and you could scale it up probably to larger sigma values than you could for the Euler scheme. So in this way, by using the method of lines, so by considering a spatial semi-discretization, you can actually kind of test different combinations of spatial discretization, which gives you a modified wave number, and temporal integrations, which give you the limit in which the spatial discretization needs to be located. But it's all kind of based on the same principle, namely a Fourier transform of your solution. So it all has the same conditions associated to it. It needs to be linear because you consider each mode independently. It needs to be well, it needs to be linear. It needs to have no boundary conditions because you do a Fourier transform, so it has to be periodic, and so on. Okay. Do you have any questions to that? To kind of how we combine temporal and spatial discretization? Okay. Then I just have one last point that I would like to make regarding stability and in particular amplification factors. Because as I was saying, that this amplification factor is actually a quite important concept for time integration, or for the characterization of integration schemes. So therefore, I would like to mention one more aspect here, and that's related to the characteristic equation, which we have also mentioned before. So if we assume that this set is lambda times delta t, as we have introduced before, then we have seen earlier that for the explicit Euler, my amplification factor, so un plus 1 divided by un, so g of z, has been something like this, 1 plus z. This we have said before. And also what we derived is that for the implicit Euler, the g of z was 1 divided by 1 minus z. So this is something that that we have derived. I think it was last hour or last lecture. Also, we have not derived it, but it's quite straightforward to do for the Crank-Nicholson scheme, which is a combination of the explicit and the implicit Euler. This transfer function or amplification factor g of z will be 1 plus z divided by 2 divided by 1 minus z divided by 2. So this is, if you want, you can consider this to be a homework, but you can also just believe. You will use this scheme or have used this scheme in homework number 2 already. Okay. Now, why do I write that down? Well, I would actually like to show you the following, because it's actually quite instructive to plot these functions in the following way. So if I plot here, well, this is as usual the real part of Z, and here we have the imaginary part of Z. And now I would just like to plot I would like to plot actually this is not correct. Sorry, no, I messed up something. So I'm sorry. This one here should be the Z being lambda times. So this is the value of Z, and here you would have the G of Z. I'm sorry. So like this. So this is the absolute value. Now, what I would like to plot here, it's actually not, it's just G. So sorry, I got confused. So I would like to plot now the explicit Euler, the implicit Euler, and the G of Z if I just assume lambda to be a real number. Okay, so not a complex one, but just a real number. So that would mean that I would plot, for instance, 1 plus Z, which would be kind of a line like this, for instance. So this would be for the explicit Euler scheme. Now I can plot it also for the implicit Euler scheme. So 1 divided by 1 minus Z. And that will be something that looks like this, perhaps. I need to be a bit careful that I'm plotting it well. So this would be probably something like this. It should actually go through that point. So this would be the implicit Euler. And then the last line, which I could plot in blue, would be for the Crank-Nicolson scheme, which would be something like this. This would be for the Crank-Nicolson scheme. Okay, so now why do I plot this, really? Well, now the interesting thing is that because we have here the amplification factor, so we can actually give some limits of where the integration is in fact stable. And of course, the limit is to be at +1 and at -1. So this is at +1 and this is at -1. Outside of this, of the red lines, the integration would be unstable. Whereas it's inside, it would be stable. Because the amplitude, or G, is larger than 1 or lower than -1. So that means, and I guess that this is now pretty clear, everything that is in the positive half side here, so when lambda times delta x is positive, is of course unstable. And this we knew. We also now know, or we can realize, that everything that is inside the red bits on the left side is stable. And here we see that it's only the explicit Euler scheme that actually leaves here the stable region. And of course, that is located at -2. And this we know from the circle from before. The two other schemes that we indicated here, so the purple one, which is the implicit Euler, and the blue one, which is the Crank-Nicolson, they all stay within the two red lines. But they are very different, in fact, because the purple one approaches 0, whereas the blue one approaches -1. And of course, that's a different asymptotic value. If you think of a Z or a lambda, which is very negative, for a lambda going to -infinity, this is very different. And of course, now the question is, how does the exact solution look like? Solution. Because that gives us an idea of what is actually the correct solution, perhaps. And this is now the last thing that I would like to plot in here. And I just plotted here with this pink color. The exact solution would actually be, well, we can write it down. The exact thing would be g of z being, well, e to the power of z, right? That's the exact solution. And if I plot this, the exact solution would be something like this. So you will see from this that the exact solution actually approaches 0 for -infinity. And of course, that means that for stiff problems, and that's what you also looked at on the homework. So for stiff problems, which means that z is going to -infinity. Well, for the implicit Euler, we had the situation that g of z going to -infinity is actually 0, which is the same as the exact solution. Same as exact solution. Whereas for the Crank-Nicolson, the situation is that g for z going to -infinity is -1. And that is not the same as the exact solution. -1, in fact, means that this gives you an oscillatory solution, which is typically not what you want because it starts to wiggle. Okay. So this was the final thing that I wanted to show, how you can also use the amplification factor to kind of understand how the solution behaves when you go to extreme values of the amplification factor. Okay, with this, I would like to close for today and thank you for your attendance. The next time we will see each other is tomorrow. Okay, thank you very much.